Aloha! Calc 3, Math 263. A. Here we go. The dot product. Dot. All right. So the dot product. Okay, we're going to need this for a lot of our extensions and application problems in Calc 3. So it's a new operation, okay? And it's when we put a little dot that kind of looks like a multiplication symbol in between two vectors, okay? And our result when we do the dot product is a scalar, okay? That's why it's also called a scalar product, or some places will call it an inner product. And all the dot product is you multiply your A's, add it to your, multiply your first component, add it to your second components being multiplied, add it to your third components being multiplied. All right, so hit pause real quick. See if you can get this correct. I think it's helpful to always write this, in the component form. So that'd be what, 1, 2, -3, dot. No I, so 0 to -1. And all you have to do is multiply the first components, and your answer is going to be a scalar, so we get rid of those chevrons, right? We get rid of those bad boys. +4, and I get, +3, and I get 1, 2, 3, 4, 1, 2, 3, 4, 6, shichi. You get shichiban. Okay, we get a 7, which is a scalar. Okay, thus called the scalar product as well. Okay, but that's all the dot product is. All right, so we have some properties of dot products. Now, you guys all know we do these proofs in class. What I would like you to do is you're going to try number 1 on your own, and then our second example here is a little bit longer. Try 3. If everybody does not have 1 done when you walk in class next, we will have a pop quizzy quiz. All right, find the objective 13. Find the angle between two vectors. Okay, we have a little formula that allows us that if we have two vectors, say A and B, okay, obviously if we connect those two guys from the previous section, A plus the opposite of B, we get that angle right there. Okay, and that's the angle between the two vectors. And if you can find the angle between the two vectors, then you can easily find it knowing what the two vectors are. So we have our little theorem here, and if you just solve for cosine of theta, you get that equivalent, or the corollary. Corollary is like just like a sub of the theorem, and that's just solving, right, for cosine theta. So what would be awesome right now is if you had paused and figured out if you could find that angle without my help. I mean, that would be absolutely fantastic, awesome. Okay, so hit pause, then come back and see if we get the same thing. I always work better, when we put them in these chevrons, put them in component form. Okay, and then we've got vector v, -3, 6, and 2. And this is really just formula stuff. And these are formulas that you do have to memorize, so make sure you're very careful. Now, since it's asking me for the angle, I am going to use the corollary, which would be cosine of theta is equal to u dot v, right? It's a dot product between those two vectors, all over the magnitude of u times the magnitude of v. Now, if I don't put a dot there, then it helps to know that that means multiplication. Okay, so that means cosine of theta would be equal to, what would that be? That would be -3 minus 12 plus 4 all over, that'd be square root of what? That'd be 1 plus 4 plus 4. Multiply that by what? That'd be 9 plus 36 plus 4. If I keep on coming down here, that gives me a little cosine of theta is equal to -15, -11, and that'd be square root of 9, which is 3. That'd be what, 49, which is 7, so I get -11 over 21. So theta would be equal to the, right, this would be a calculator question. If not, you could leave your final answer like that, which I have theta in degrees being 121.6. I forgot to get the radians of that, but you could easily do the radians of that. Actually, let's make sure we have complete notes. I've got my little calculators right here. And if I go a little inverse cosine of -11 over 21, I get radians to be 2.122. Okay? Or you could get the degree, depending on what the question asked. Okay? But that's all you have to do to find the angles between two vectors. I actually think the toughest thing right there is making sure you know that formula. Okay? All right. Let's see what's next. Interpret the sign of the dot product. So when you're doing these dot products, you can get a lot of these different cases. I kind of have the pictures right here drawn from you that I was able to get from the book. But if you take the dot product of your vectors a and b and you get something that's greater than theta, then that means your angle would be acute. Okay, angle is acute. Okay, this is just us taking good notes here. You guys don't have those pictures. If you want to keep the pictures with it, please do. Okay, if you do the dot product and get theta, if a dot b is less than 0, then theta is obtuse, and take a guess. If you take the dot product and it's equal to 0, then that means your theta is a right angle. Okay, or the two vectors would be perpendicular to each other. Okay, how can you tell whether or not two vectors are parallel? Well, we would say if the vectors are scalar multiples of each other. Okay? And what would it mean? What would an example of scalar multiples of each other? Well, let's say you have a scalar, a little example here. Let's say you have a scalar -1, 0, -2. Just let's multiply all those by 3. So -3, 0, -6. Those two vectors would be parallel to each other. Okay, try finding the dot product of those bad boys, see what happens, huh? That's what I would be curious of. I've got one little other extra practice, okay, if you want it. You have these two vectors, 2, -1, and 5, -4, 2. And it just says show that they're perpendicular. Well, what's an easy way that I could show two vectors are perpendicular? Well, if I take the dot product of them, 10 minus 8 minus 2, and if the dot product of them 0, I know those vectors are perpendicular. Yes, yes. Okay, as easy as that. All right, remember, you're going to be using all this information and all of the homework that we're going to do in class. Okay, all right, we have something called direction angles, alpha, beta, and gamma. That's a new dude, Greek term meaning gamma. It's like the fish going backwards, right? Alpha, you kind of do like a little fishy, that's boom. That's called gamma. Gamma are the angles those are the angles that a vector makes with the positive x, y, and z axis. Okay? Their cosines are also called direction cosines. Okay? Cosine of alpha is the dot product between the vector A and your vector I. Remember, I is 1, 0, 0, okay, in 3 space. And then you divide that by the magnitudes of both of those vectors. Okay? Just like cosine of beta would be equal to your vector A, but this time you would dot it with your j. Remember, j is 0, 1, 0. Okay, and then you would divide that by the magnitudes of your vector A and your vector j. But remember, I, j, and k, if you take those magnitudes, it's simply the square root of 1. Okay, which is 1. Ichiban! And then cosine of gamma would be equal to that third component, right? Why the third component? Because it would be your vector A multiplied by jk, k, which is 0, 0, 1, so that it would just be the third component, right, divided by the magnitude of A. Once again, magnitude of A times the magnitude of k, in this case, the magnitude of 0, 0, 1 would still just be the square root of 1, which is ichiban. Okay, a couple things to note. All right, almost like the Pythagorean theorem. We have one for cosines in 3 space. That cosine squared of alpha plus cosine squared of beta plus cosine gamma squared would be equal to 1. Okay? Another note would be that your vector A is equal to the magnitude of A times cosine alpha, cosine beta, cosine gamma, which can also be expressed, right, if we divide that magnitude over, that cosine alpha, beta, and gamma are all equal to your vector A over the magnitude of A. So, what does that tell us? The direction of your cosines form, right? What is that right there? That's something that we should always be really, really familiar with. It's our unit vector. Remember, that's our little formula to find the unit vector in the direction of A. Right? And then our alpha, beta, and gamma will give us our direction, okay, of A. Boom. Okay, so example 3. Let's put this into some use here. Find the direction cosines of our vector A. I always like to do that just because it doesn't always come up clean. and approximate the direction angles to the nearest degree. Well, in order to do this, right, you guys, I need to know what the magnitude is, since I already know the vector. So the magnitude would be 2 squared, which would be 4 plus 16 plus 16. That'd be the square root of 36, which is 6. Okay, so if I just set up my little formulas here, that means cosine of alpha would simply be equal to, right, what would it be equal to? Well, if we look at our formulas that we wrote down above, it'd be your first component divided by the magnitude. And because remember, we're really dotting vector A with my vector I, right, which would be out in the x-axis direction, which would be 1, 0, 0, and we would get that, and thus I could find alpha, and that ended up being about approximately 71 degrees. Cosine of beta then is simply equal to the second component divided by 6, which that means beta would be approximately equal to 32 degrees. I already did this already, you guys, okay? Make these notes a little bit quicker. And cosine of gamma gams would be equal to 4 over 6, or 2/3, and that means gamma gams would be equal to approximately 48 degrees. All right, here we go. An example that is pretty cool is, gosh, I gave the picture. We should be able to draw that picture, but all of these guys being A, so your vector would be A, and A. All right, you can find the angles, right? The angle between vector A and our I vector would be alpha, with our J would be beta, and with our K would be gamma. Okay, and so this example 4 says to find the angle between the diagonal of the cube and one of its edges. So let's go ahead and do that vector A and the x-axis. Okay, let's go ahead and find that alpha there. Well, how would I do that? Well, I would go ahead and let's label our vector A, right, which would be A, comma, A, comma, A, okay? The magnitude of that, right, because we're going to need the magnitude in order to find the cosine direction, right, if we wanted to find that angle, would be a squared plus a squared plus a, and then the square root of that, so it would be 3a squared. So all I have to do now is a little cosine of alpha. Why? Because I'm doing it with the x-axis, we said, and that would be equal to a over the square root of 3a squared, which would be equal to 1 over the radical 3, which means alpha would be equal to 0.955. If we are in radians, I did this one for you guys, or alpha would be equal to 54.7 degrees. Okay? All on whether they're asking for radians or degrees. Okay, if I don't ask, then I technically would have to accept both answers, but trust, then I'm going to ask. Okay. All right, now this one always seems to cause a little bit of trouble. This projection of B onto A, or it always, for some reason, or the component of B onto A. Okay, these always seem to cause some trouble. So let's make sure we're okay with it, all right? So we're going to draw a picture here to help us out. Okay, let's say we have a point P, and we have a vector PQ. Okay, we'll call that vector A. And then let's say we have a vector R here, and we'll call that B. Okay, and let's say for a lot of these problems that we're dealing with, and we're going to get into work in a moment, we want to know what a projection of B onto A is. And a projection of B onto A is the following, okay? We always use a right angle here, okay? And we're going to project that vector PR or B onto vector PQ, onto A, okay? And it's almost like it would create, you know, that blue vector right there. And that blue vector right there is what we call the projection of B onto A. That's what we call that, okay? And it's a vector, okay? That vector actually has a magnitude, okay? The magnitude of that is what we call the component, okay, of B onto A, or that ends up being a scalar, okay? And it's, or you could say it's a scalar projection of B onto A. So there's two things that we need to be really, really good at. So we're going to define a couple of these, okay? And that is the component of B onto A is equal to the magnitude of B times cosine of theta. Now, we're going to simplify this a little bit. And if we go back to the previous notes that we did, we wrote down that cosine of theta is equal to A dot B all over the magnitude of A times the magnitude of B. Remember, we used that in a previous problem that we did. Okay, now if we do a little splings, that is equal to A dot B. And we're just simplifying this so it's easier to use and get answers for it. okay? And then what that means is our most simplified form of the component of B onto A would be A dot B, those two vectors, dotted over the magnitude of A, okay? And the projection of that then would be your component or your scalar, okay, of B onto A. Ooh, I've got to move my face, which would be A dot B, A dot B all over the magnitude of A. And then all you would have to do is we want to represent that projection of B onto A, so I just need a unit vector. And a unit vector will give me in that same direction, which would be A, vector A, over the magnitude, which you could simplify this into being A dot B, right? Remember, that's a scalar. We have two of those magnitudes on the bottom, so we're going to square that, and then we're going to multiply it by our vector A. Okay, so this would give you a scalar, okay, but since I'm multiplying it by my vector A, the projection of B onto A will actually be a vector, and it would be that guy right there, okay, which would have a magnitude and a direction. Okay, we get the magnitude by doing our component, our scalar, and then we get the direction by finding the unit vector, which would have that same direction. Okay? Pretty cool if you ask me. And so I want you guys to try an example here. I want you to hit pause and see if you can get the answer. I want you to find the scalar component of B onto A and the projection of B onto A. Okay, if your vector B is 1, 1, 2, and your vector A is -2, 3, 1. All right, see if you can do that. Okay, hit pause. Let's see if you got it right. So first what I need to know is what the component or the scalar of B onto A is. And then in order to do that, let's use our most simplified formula, which would be the dot product of the two vectors over the magnitude of A. Okay, and remember the form, that's the component of B onto A. Okay, so A goes in the bottom, just like A goes on the bottom there. That's kind of how I remember what to do. So if we dot these guys, I get -2 plus 3 plus 2 all over, whether it be square root of 1. Ooh, I almost did it wrong. Square root of 4 plus 9 plus 1. So that would be what? That would be tree over the square root of 14. So that is your scalar. And in order to get the projection of B onto A, okay, I would multiply that by the component or the scalar, right? And then do you remember what we did? It is simply, but we would square that down there and then multiply it by vector A. -2, 3, 1. And so if I want to simplify that, what do we get? We get -6 over 14, we get 3 over 14, and we get, 9 over 14, and we get 3 over 14. Boom. Darn it. Kind of ran into my face there, okay, you guys? But I think you're okay. -6 over 14, 9 over 14, 3 over 14. Okay, hopefully you were able to do that without my help. Last but not least, right, we're trying to make these videos as short, easy peasy as we can. And now we're going to do work, which is equal to your force vector, dot, right, dotted with your D vector. Okay, I'm going to use, I know a lot of books use a little capital D, so we're going to go sheblang and sheblang. Okay, so it's your force vector dotted with your D vector. Now, why is that the case? Well, I got a little bit of some stuff I want you to write down, all right? So let's start with P again. Okay, we're going to go out here in Q. We're like the famous example they start with work and these vectors and these projections and all that craziness is they start with like, hey, we're trying to pull a wagon. Okay, and we go off here on R. Okay, we're trying to pull Mr. Sola that's chilling in a wagon. Okay. All right, so here we go. So we got our force vector there. Okay, we're pulling with some force. We're not pulling it horizontally, right? So it's like having a wagon, and we're pulling them on that thing. Okay, if you notice, there will be, I should have kept my color coded correctly. We have this projection. Let's call that S. We have obviously an angle there. That distance from P to Q we're going to call D. Okay, that vector D, we're going to call that displacement. So it goes hand in hand with the formula that we just wrote down. And that, believe it or not, means work. Okay, your work is going to be equal to the magnitude of your force times cosine theta times your magnitude of your vector D. Okay, now you're going to say, like, what the heck? That is simply equal to this, right? Just little commutative property, okay? And then we learned, if you go back a couple of notes, that this actually right here is equivalent or equal to this. And that's how it's created, the dot product of those two vectors. So there's two ways you could do these problems when dealing with work. Okay, you can deal with magnitudes and angles, or you can simply take the dot product of them. Why? Because they're equivalent to each other, right? We learned that last section when we said cosine theta is equal to f dot d over their magnitudes, okay? And we learned that in a couple previous pages. So let's try this with example 6, okay? And then we're done for the day. That's it. Easy peasy Japanesey, right? Ooh, my bell's going to ring pretty soon, so I apologize if we're going to kind of fly through this, right? But here we go again, all right? We're pulling a wagon this way, okay? And that's going to be 50 feet, okay? And right, a wagon, it's got a handle, right? And we're going to say that that's the force being applied, and the force is 10 pounds around the handle, and we give you an angle here which is 60 degrees. And the question is how much work is done in order to move that wagon 50 feet, right? And I know you guys do a lot of these things in physics. Well, if you could have your both vectors, it would just be the dot product of those two. So the question is could I create maybe two vectors, make this problem easy peasy Japanesey, or since they gave me an angle, maybe I should use the angle here, right? So I could actually, right? Because we do know what our force is, right? We're going to have to pull this guy. Oh, I'm sorry, we know what our D is, right? We're going to have to pull that guy 50 feet. So I'm going to dot that with 50, 0, right? Because if you think about it, you move 50 on this way. If we're talking about two dimensions here, we're going to move that 50, and then that would be the X component, or the I component, right? And then you have your J component being 0. Okay, so then now I need something to represent our force here. Well, our force here, if we go back, to our previous notes, would be equal to the magnitude of that force, which would be 10, okay, times cosine of theta, sine of theta, which are both 60. So I could distribute that in. Cosine of 60 degrees is a half, so believe it or not, that would just be 5, 5 radical 3, and I'm going to dot that with 50, 0. And believe it or not, if you dot that, it does all of the work for us. I don't know about you, but that gives me just 250, and it'd be feet times pounds. Boom, that's it. Easy peasy Japanesey. Okay, make sure you do that proof so we don't have a pop quiz. Alohas.